In this video, we continue with Chapter 5. We'll be covering Chapter 5.4, all about mathematical models and the least squares analysis. We have two learning objectives. We are going to find the orthogonal complement of subspace. So that will be covered in this first video. And in our second video, we will see how to solve a least squares problem. I am first in this video going to introduce the least squares problem because that's going to help us build our understanding of the orthogonal complement. And then in the second video, we'll see how to solve a least squares problem. So in this section, we are considering inconsistent systems of linear equations, and we find the best approximation to a solution. Now, remember back from Chapter 1, when we say inconsistent solution, we're talking about a linear system that has no solution. So we are going to try to best approximate a solution because this is what happens with real data much of the time. Okay, so here's the example. I had a white box here before by mistake, but now my example should be showing up for all of us. So given this table of data over here, and we're using t and y, but you could think of it as x and y, we want to find the coefficients c naught and c1 of the line y equals c naught plus c1t that best fits these points. So if you take a look at the graph over here, there is no perfect fit line, but the points are close to a line, so we can find what we call the line of best fit, or what we know of as the linear regression line, or what we call the least squares linear regression line. So the system of linear equations that we have to solve comes from plugging the 3 points, ti, yi form, so you've got t1, y1, t2, y2, and t3, y3, into this equation. C naught plus C1 equals 0, C naught plus 2C2 equals 1, and C naught plus 3C1 equals 3, where these are our T values here, and our Y values are the output. And so we know from Chapter 1 that we can form a matrix with the coefficients and multiply that by C naught and C1 and put that equal to our solution, our y's, 0, 1, 3 as a column vector. And then we know we can solve that to find C naught and C1. So this system, when we go to solve it though, because it's not a line of best, because it's not a perfect line, we get an inconsistent solution. So the reduced row echelon form looks like this: 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so we also knew that there would be no solution because the 3 points in the graph are not what we say collinear or perfect fit. So what we want to find is what's known as the best approximation. So recall that AX equals the coefficients 1 times C naught plus the values 1, 2, 3 times C1, where the 1, 2, 3 are our T values. So this AX is always in the column space of A. However, AX equals B has no solution, so B is not in the column space of A. So we want to find an X that gives the AX that is closest to B. So this idea of closest is our idea of the best fit. So this is what we think of as our least squares problem. So given an m by n matrix A and a vector B in Rm, we want to find X in Rn such that this Ax minus B norm squared is minimized. So here's the visual. So here's vector 1, 1, 1 over here. And here's our AX here. Here's vector 1, 2, 3. And then here's B up here. So this distance, AX minus B, the norm of AX minus B is here. We square it because if we get a negative, we want to think about overall the absolute distance. So we could also do the absolute values, but in computer coding, typically it's faster to square values. So what statisticians have relied on is squaring. So this is called the least squares because we're trying to find the least square of the distance. So this is going to give the AX squared instead of just the norm of AX minus B. Because the norm of AX minus B typically involves a square root. So intuitively, we see that AX minus B is orthogonal to the column space of A. So you can see here's A down here in, call it the XY plane, and then the distance AX minus B is in the Z direction from this diagram we have. So we're always going to have a orthogonal relationship here. So that's why we're going to get into figuring out orthogonal subspaces and define the orthogonal complement. And then we're going to use these new skills about orthogonal complements in service of solving this least squares problem in the second video. Okay, so to solve this least squares problem, we're going to build up this concept of orthogonal subspaces. So we're going to let S1 and S2 be two subspaces in an n-dimensional vector space V. So we know S1 and S2 are orthogonal when the inner product V1, V2 is 0 for all the vectors V1 and S1 and all the vectors V2 and S2. So now we're going to define what's known as the orthogonal complement. So the orthogonal complement of S1 is a set S1 with this little upside down T symbol. It looks kind of like the perpendicular symbol. And that's going to be equal to all the U's in V such that the inner product of U and V is 0 for all vectors V in S1. And so we pronounce this orthogonal complement as S1 perp because the little symbol looks like our perpendicular symbol. So if every vector X in the vector space V can be written uniquely as a sum of vectors S1, a little s1 from the set S1, and a vector lowercase or little s2 from the set S2, then X for any arbitrary vector X is going to be a sum S1 plus S2. Then we say V is the direct sum of S1 and S2, and we write vector set V equals S1 direct sum S2, and this plus with the circle around it is what's known as the direct sum symbol. So let's look at an example. So if we want to see an example of orthogonal subspaces, S1, which is the span of the vectors 1, 0, 1, and 1, 1, 0, and S2 equals the span of the vector -1, 1, are considered orthogonal because the dot product of any vector in S1 and any vector in S2 is 0. You could verify to see that. We're going to get cancellation here from the calculations. And you can see that because there's this -1 in the first vector in S2, so that'll negate either of the vectors in S1 because we've got a negative and a positive here that's going to get multiplied by, and the same for the second vector. So let's look at an example of finding the orthogonal complement. So we're going to see here how to find the orthogonal complement of the subspace S of R4 that's spanned by these two column vectors V1 and V2 that together form this matrix A. So V1 is 1, 2, 1, 0, and then V2 is 0, 0, 0, 1. So a vector U in R4 is the orthogonal complement of S when its dot product with each of the column vectors of A, V1 and V2 is 0. So the orthogonal complement of S consists of all the vectors U such that A transpose multiplied by U equals 0. So here are the vectors V1 and V2 in matrix A here. I transposed it, so that's why we've got row vectors instead of columns. So this is A transpose here. And here's U. We'll represent U as x1 through x4. And then we set this equal to 0. So we can say, well, that is the orthogonal complement of S is the null space of the matrix A transpose. So S perp, or the orthogonal complement of S, is going to be the null space of A transpose. So using the techniques for solving homogeneous linear equations that we saw earlier in chapter 5, you can find that a basis for the orthogonal complement is going to consist of these vectors. U1 is -2, 1, 0, 0 transpose. And then U2 is going to be -1, 0, 1, 0 transpose. And we could have written them as column vectors like this. We just had a little more space here. So you can see -2, 1, 0, 0, and -1, 0, 1, 0. Okay, so remember back from, it was actually section 4.6, not earlier in chapter 5, the way that we would find the basis for the null space is to take our matrix A, convert it, or A transpose in this case, convert it to reduced row echelon form, solve those equations, figure out what the free variables are, our S's and our T's, and then use the coefficients for those S and T to find our basis vectors here. So that's how these basis vectors U1 and U2 came about. So you could work through that as practice. You've shown me in lab assignments and other assignments that you can calculate these just fine. So you can go back to your chapter 4.6 notes and do some more work through this if you want to do some more practice. All right, and then recall from our definitions over here, the direct sum is when S1 and S2, all their every vector x and v can be written as a unique sum of a vector from S1 and a vector from S2. So then we say V is a direct sum of S1 and S2. So let's look at some examples of direct sums. So R3 is the direct sum of these subspaces S1 and S2. And so you can see every vector in R3 can be written as a unique combination of vectors from S1 and S2. And then similarly, R4 is the direct sum S plus S perp, where S is the span of 1, 2, 1, 0, 0, 0, 1. And then S perp is the vector that we just found, or the span of the vectors that we just found. So the span of -2, 1, 0, 0 and -1, 0, 1, 0 that we found back here in the example of finding the orthogonal complement. All right, so let's look at some properties of orthogonal complements. And one more point we want to make also is when you have the orthogonal complements, the only vector you have in common between S1 and S2, so if we come back here to our examples of the orthogonal complements, the only vector in common is the 0 vector. So if you look back at our orthogonal subspaces, you can see that in general for S1 and S2, their intersection here, where S1 is the span of 1, 0, 1 and 1, 1, 0, and S2 is the span of -1, 1, their intersection, the only vector in common is that 0 vector. Okay, so back to our properties of orthogonal complements. So we're going to let S be a subspace of an n-dimensional vector space V. Then the dimension of S plus the dimension of S perpendicular have to add up to the dimension of the vector space, right? Every vector can be written as a component of a vector from S and a vector from S perp. So the dimensions add up to n. Then our vector space V is a direct product. I'm sorry, a direct sum of S and S perp. And then, of course, the complement of the complement just takes you back to vector space S. So you can say, okay, S perp is S, or the complement of the complement is the original set S. So let's take a look at an example that'll help make this a little more concrete. So we're going to work in R3. Well, what's the orthogonal complement of R3? Well, that's just the 0 vector. And then the orthogonal complement of R3 is the 0 vector, and then the 0 vector's orthogonal complement is R3. So let S sub x be the span of our favorite basis vector, E1 or 1, 0, 0, and then Sy is going to be the span of our second basis vector from our favorite standard basis, 0, 1, 0, and then Sz will be the span of 0, 0, 1, our third favorite, or our third vector in our favorite vector space. And remember, when we say these vectors span Sx, Sy, and Sz, to span is when every vector in V can be written as a linear combination of vectors in S. So when we say S sub x here, that means every vector in S sub x can be written as a linear combination of the span of 1, 0, 0. So basically all the x values along the x-axis, and S sub y is the span of 0, 1, 0. So that's anything along the y-axis, all the linear combinations, and S sub z are all of the vectors along the z-axis. So then Sxy is going to be the span of 1, 0, 0, and 0, 1, 0. So these are all the xy combinations, so everything in the xy plane. And then Syz are all the vectors in the yz plane, because see how we've got x is 0 here. And so then Sx is orthogonal to Sy, and that makes sense because we know the x-axis is orthogonal to the y-axis. And Sy is orthogonal to Sz because we know the y-axis is orthogonal to the z-axis. But notice that Sxy is not orthogonal to Syz because we're thinking about the xy plane and the yz plane. So imagine if you did the dot product of elements in Sxy and elements in Syz, you're not necessarily going to get zeros there because Sxy, you got the 1 here in the y, and in Syz, you've also got a 1 there in the y. So you wouldn't get the 0 if you did the dot product there. You can sort of visualize it, thinking about every element in the perpendicular to vectors are not necessarily all perpendicular. So then Sxy is going to be the sum of S sub x plus S sub y. And then S sub z complement. So this is now just the z-axis. So if you think about that, oh yeah, the orthogonal complement to the z-axis is going to be the xy plane, because the xy plane will always be perpendicular to the z-axis. And then similarly, the orthogonal complement to the xy plane is the z-axis, because that line through z is always going to be perpendicular to the xy plane. Okay, so this brings us to theorem 5.16. This is the theorem about the fundamental subspaces of a matrix. So we're going to let A be an m by n matrix. Then this notation R of A means the column space of A. This R stands for range. And then R of A transpose is the row space of A. And N of A we know is the null space of A. So R of A transpose, the row space of A, and the null space of A are orthogonal complements. That is saying all vectors in the row space of A are orthogonal to all vectors in the null space of A. And so we can verify the dimension of the row space of A, R of A transpose, plus the dimension of the null space of A equals N, the dimension of the vector space. And we can say the row space direct sum with the null space is going to make up Rn. And so the column space Ra and the null space of A transpose are orthogonal complements. So we can say all vectors in the column space of A are orthogonal to all vectors in the null space of A transpose. And so we're having to use a transpose here because remember, the transpose would swap the rows and the columns. So we have to do that to get the orthogonality between the column space and the null space. And then the dimension of the column space plus the dimension of the nullity of the transpose matrix is going to be M. Remember, this is an M by N matrix, so M is the number of rows and N is the number of columns. And so the column space of A plus the null space of A transpose is going to equal Rm. So here's a sketch of the proof. So the null space of A is all the x values in Rn such that Ax equals 0. And so that shows that the null space is orthogonal to the row space because the null vector x is orthogonal to each row of x. So saying Ax equals 0 is equivalent to saying row 1 of A times x equals 0, row 2 of A times x equals 0, all the way through row M of A times x, I'm sorry, dot x equals 0. So these are dot products. I said times, but I meant dot products because you'd multiply and then add up for each element. All right, and then the dimension of R of A transpose, that is our row space of A plus the dimension of the null space equals N is just good old rank plus nullity that we saw back in chapter 4 and 4.6. And so we already know that. So the basis vectors of the column space, the row space, R of A transpose is the row space. So the basis vectors of the row space are linear independent of the basis of the null space because they are orthogonal to the basis of the null space. So the union of a basis of the row space and a basis of the null space is going to be a basis of R because they're orthogonal. So we can say the row space of A plus the null space of A equals Rn. And then for the second proof, you just replace A with A transpose in part 1, and then use the fact that A transpose transpose is A itself. And then when we replace A with A transpose, we have to interchange M, the row count or the row dimension, with N, the column dimension. Okay, so let's work through an example. We're going to find the orthogonal complement of S, where S is the span of 1, 2, 0, 0 and 0, 1, 0, 1. And so this is that same example we did earlier. I'm just going to walk you through all the steps here. So S is the column space RA. And so here are our columns in the matrix. So S perpendicular, or the orthogonal complement to S, is the null space of A transpose. So to find the null space of A transpose, we're going to solve AX equals 0. So we take A transpose here. I think there should be a T here. We're going to take A transpose, and then we go to our reduced row echelon form. And then we solve this in terms of our free variables. So from that first equation, we've got 1x1. We've got nothing for x2, nothing for S. So this is going to be column with x1. This is going to be the column with x2. This will be the column with S. And our first column will be the columns in terms of T. And then we've got negative 2t equals 0 up in the first row. And then in the second row, we've got 0x1 plus 0s, because we got zeros here in the S column, plus 1t equals 0. So we're able to solve that to say, okay, x2 is going to be negative t based on the second equation, and x1 is 2t based on the first equation. So then when we write our solution out, we've got x equals 2t minus t, right? Because this is x1 and x2. And then we said x3 was s and x4 was t. And then we split those out into the column vectors associated with s and t's coefficients to find the null space here. And so it's going to be s times 0, 0, 1, 0, because we've only got s here for x3, plus t times 2, negative 1, 0, 1. So this is how we got earlier that our S-perp, or our orthogonal complement of S, is the null space of A transpose, which is the span of 0, 0, 1, 0, and 2, negative 1, 0, 1. So in the next video, we are going to see how to solve the least squares problem.